Sathyabama Institute of Science and Technology.
Hi everyone, I'm Dr. Mercy Paul Selvan, Professor, Department of Computer Science Engineering, Sathyabama Institute of Science and Technology. In this video lecture, we are going to see about shortest remaining time first algorithm. The acronym is SRTF, which is Preemptive SJF. To start with, we are going to see what is process. Process technically can be concluded as program in execution. Right now, a program, any program in execution time, we call a program as process. So, as the name suggests, it is an active entity. It requires various resources in order to accomplish the task, and it is associated with PCB. Every process is associated with PCB. The expansion of PCB is process control block, where all the in and out details of a process would be stored as a data structure. We will see what are the process state. We have 5 states. First one is new state. Whenever a process is created, we call that state as a new state. When a process is created, it will be into a ready queue. It will be entered into a ready queue, and it will be waiting for the resource, especially for CPU cycle, and it could be allocated by the program called scheduler. It's one of the operating system entity. Once the resources are allocated to a particular process, then it will turn into running state, where the process will be running exactly. Once the task is over, it will be switched over to exit state, where we call the state as terminated state. In between, while running, in between, if any IO operation is in need by the running state, or if any event wait occurs, then it will go back to waiting state, where it will wait. Whenever IO operation is over, the event is completed, then it will be back to ready state, where again it will be waiting for the scheduler to schedule the particular process by giving CPU for the process. Let's talk about preemptive scheduling. In preemptive scheduling, this particular scheduling is used when a process switches from running state to ready state, or from waiting state to ready state. As I mentioned earlier, all the processes initially would be in the ready queue. Once CPU cycles are allocated to a particular process, it will be switched to running state. If CPU cycles are allocated to a process which is in the ready queue, when it moves into a running state, it is getting executed. Right now, the running process is being executed. By the time any process with the least shortest burst time, then this particular running process must be preempted. That means must be stopped, and the new process should be taken. And the scheduler will allocate CPU to the new process, because the new process has got least burst time. But in the case of non-preemptive scheduling, it is not so. Once the CPU is allocated to a running process, though some other process enters into a ready queue with least burst time, even then the running process will not be stopped. It will not be preempted. That's why we call this as non-preemptive scheduling. The entire burst time should be given to the CPU cycles must be allocated for the entire burst time for a running process. Now we are going to see some important terminologies. First, burst time. What is burst time? Burst time is nothing but the time required to complete a particular process. So, the time taken by a process in order to complete the task. Now, arrival time. Arrival time is nothing but at what time a particular process, at what time it entered into a ready queue, it arrived. Waiting time is nothing but how long a particular process waits in order to get the CPU, in order to move to running state. Turnaround time is nothing but the time taken, the overall time taken for a process which includes waiting time as well as burst time in order to complete the job. So, your turnaround time is equivalent to waiting time plus burst time. Let's see preemptive SJF, which is nothing but shortest remaining time first. We know what is preemptive algorithm. Whenever a new job is entered with least burst time, the running process must be preempted and the new process must be given CPU. This is the concept of shortest remaining time first. In our example, we have 4 processes P0, P1, P2 and P3. Respective arrival time is given, respective burst time is also given. Now, who has arrived first? P2 has arrived first into the ready queue. So, at 0th second, P2 enters in the ready queue by the time no process is available in the ready queue. Because no process is not available in the ready queue, P2 takes the CPU. Scheduler is giving CPU to P2 process. After 1 second is over, P3 is entering. We have to check out the burst time. For P2 burst time, it is 6 milliseconds. After 1 second job is over, the remaining time for P2 is 5 milliseconds. By the time P3 is entered, because arrival time of P3 is 1, P3 is entered into the ready queue with lesser burst time. Now we need to compare the remaining burst time of P2 and the exact burst time of P3. Since P3's burst time is lesser than the remaining time of P2, it should be preempted. Why? We are following preemptive SJF. So P2 should be preempted, P3 should be given CPU now. After 1 second over, now P1 is entering, we have to check out the burst time 4. By the time after 1 second is over, P3's remaining time would be 3. When I compare 3 with 4, P3 has got lesser burst time. So we don't need to preempt because P3 after 1 second job is over, 3 milliseconds is remaining time for P3, while comparing P1 it is 4 millisecond. So it goes on. So P3 is given CPU. Alright. Once it is over after 4 millisecond, by the time everyone is entered, but when you compare the burst time, it may be equal or greater. So P3 gets the CPU. Okay. So it carries on till P3 is over. The CPU is given to P3. Once P3 is over, by the time P0 would be in the queue as well as P1 is also would be in the queue. While comparing P1 and P2, we have P0 as 2 burst time, 2 millisecond as burst time. So P0 is given chance. Now CPU is given to P0. After 2 millisecond is over, P1 is given because 4 milliseconds. So 4 millisecond P1 is given. Next P2 is given. The concept here is we compare the remaining time and the incoming process burst time. Whichever is lesser, we have to allocate accordingly. So, this example P2 has entered first. So, after 1 millisecond, the remaining time is 5. P3's burst time is 4. So, P3 is getting chance. After 1 millisecond, who is entering? P1 is entering. So, remaining time is 3. When I compare with 4, P3 gets the CPU back. After 1 millisecond, P0 is entered with 2 burst time. By the time P3 has got 2 burst time, they are equal. So, P3 holds the CPU again. After everything is over, then we have to compare the time, burst time. Whichever is getting least burst time as of now, that particular process would be allocated CPU. So, P0 is getting the CPU. After 2 seconds are over, again P1 is getting the CPU. So, for 4 millisecond, then finally, since 5 millisecond is higher than 4, last chance P2 is getting the CPU, right? Okay, this is known as Gantt chart, right? And our task is to calculate waiting time and turnaround time. Let us talk about waiting time for each and every process. Come on, we'll calculate for P0. According to Gantt chart, we have to look at the corner. This is their waiting time. According to Gantt chart, P0 waiting time is 5. But at what time P0 entered into the ready queue? P0 after 3 milliseconds. So that should be subtracted. As per Gantt chart, P0 waiting time is 5, but it arrived 3 minutes late. So the waiting time 5 minus 3, which is equivalent to 2. So actual waiting time for P0 is 2. Right? Next, P1. So when I take P1, as per Gantt chart, it is mentioned as 7 millisecond. But at what time P1 entered? After 2 seconds. So we have to subtract 7 minus 2. Okay, we have to subtract 2 from 7. So 7 minus 2 is equal to 5. So P1's waiting time, actual waiting time is 5 milliseconds. Accordingly, we have to calculate for P2 and P3. P2, as per Gantt chart, it is waiting for 11 milliseconds, but it arrived 0. So 11 minus 0 is 11 only. Like for P3, it was waiting for 1 millisecond as per Gantt chart, but P3 arrived 1 second late. So 1 minus 1, 0, it doesn't wait at all actually. So when you calculate accordingly, you will have 18 as the total waiting time. We need to divide it by number of processes. Here it is 4. So we'll get 4.5 millisecond as average waiting time. Now we have to calculate turnaround time. What is turnaround time? Which is equivalent to waiting time plus burst time. How long a particular process is waiting to get the CPU and what is its burst time to complete the task. Put together we call it as turnaround time. So average turnaround time P0. The waiting time of P0 is 2. The actual burst time for P0 is 2. So 2 plus 2, 4. Now P1's waiting time is 5. Then we have to add P1's burst time, 5 plus 4. Similarly for P2 and P3, waiting time plus its own burst time. If you calculate accordingly, you will get total turnaround time as 40. In order to calculate average turnaround time, we have to divide it by number of processes. So 40 by 4 is equal to 10 milliseconds. The challenges and features of preemptive algorithm. You have higher overhead due to frequent context switching. We need to switch from one process to other process whenever lower burst time process is entered. Preemptive scheduling waiting time is less. When you look at average waiting time with non-scheduling, if you calculate, the average waiting time is less in case of preemptive scheduling. The challenging part is starvation. We do not know when the process will get CPU because by the time process gets a CPU, some prioritized job or the least burst time job would be entered. So for preemptive algorithm, starvation is a challenging one. And of course, this algorithm is very flexible. Thank you for watching. I hope this video lecture is very useful to one and all. Thank you.